Hi all, welcome back. Today we're going to go through solving trigonometric equations. This is going to go along. We're going to go through just a number of examples. It's all about unit circle. It's all about our algebra. Now, we are solving equations, so we are trying to find a value for a variable that makes a statement true. These 6 different examples that we're going to have are going to go along lines with the first 6 examples out of the notes on the Google Classroom so that we can try them out and see how we do. Now, so for this first one, 2 sine x minus 1 equals 0. Everything, kind of the strategy right at the start is to isolate the sign. So if we come down to sine of x equals something, we can use the unit circle to evaluate that. So I'm going to rewrite this. We get sine of x equals 1/2. Now at this point, we want to find all the angles whose sine value is 1/2. Now here I do state find all solutions. That means everything. The 2 angles that are immediately on the unit circle as well as all coterminal angles. So every time we go around. So sine of x, we need the sine of some angle is equal to 1/2. That means the y value around the circle is equal to 1/2. So what I think about is, okay, sine is 1/2. It's going to be in 2 different quadrants. It's positive. That means we're going to be in quadrant 1. We're going to be in quadrant 2. Sine is the y value, so we're wondering for what angle measure is that y value 1/2. I remember my unit circle so that I know that x could be either pi over 6 or x could be 5 pi over 6. Now the all solutions comes into play in that every time we add the period, we get back to the same thing. So every time we add 2 pi, we go all the way around the circle, we come up with another solution. So rather than just pi over 6, I'm going to have pi over 6 plus 2 pi k, or 5 pi over 6 plus 2 pi k. That tells us every time we rotate once around, we get another solution. That would be a pi over 6 plus 2 pi k would be 13 pi over 6, 25 pi over 6, and so forth, as well as the negatives. We are taking that k can be any integer value. I might write it as k is an integer. I don't always need that. Take some more math classes later on, you might use that. This is what we are looking for all solutions. We have some expression that gives us everything. Number 2. Here we have an example where we are looking for something in the interval 0 to 2 pi. So we want everything, every angle that makes this work from 0 to 2 pi within one rotation. Now I see that I've got a sine shows up twice. What I'm going to do is I'm going to collect everything. I may need to factor, I may need to group. What I'm going to do is I'm going to add sine x to the other side. That happens to give us 2 sine of x plus root 2 equals 0. And we see that it is something very similar to the last one. We get sine of x equals a negative root 2 over 2. I'm thinking, okay, where around a circle has a sine value equal to negative root 2 over 2? Well, that's negative, so sine is negative in quadrant 3 and 4. I need one angle in quadrant 3. That's going to be 5 pi over 4 plus 2 pi k. Or we're going to have x equals 7 pi over 4 in quadrant 4 plus 2 pi k. Now we're only looking for those angles from 0 to 2 pi, so I need to substitute in values for k that make this work. Well, if k is 0, we've got 5 pi over 4. K is 0, we've got 7 pi over 4. As soon as k is 1, we'd be adding 8 pi. That would get us, we'd be adding or subtracting 2 pi. Adding or subtracting 2 pi if k is anything aside from 0. So if we add or subtract, we get beyond our interval. So we have our solutions. There are 2, 5 pi over 4, 7 pi over 4. Strategy, isolate the trig function. We know what we have. Number 3. Uh-oh. Got 3 tan squared. Well, forget about the square. We know how to do this. If this is x squared, we'd end up taking the square root. So again, I want to isolate the trig function. I'm going to divide by 3. We get tan squared of x equals 1/3. Here, I'm going to take the square root. So we've got tangent of x equals, now taking the square root, we are introducing the square root. So I've got plus or minus 1 over square root of 3. Now, recognizing that's something around a circle, we could also usually see this as root 3 over 3. Now, it's plus or minus. Tangents positive or negative, that could be quadrant 1, 2, 3, or 4. That's all 4 quadrants. We're looking for all solutions. So I want to think about what angles is tangent positive or negative root 3 over 3. And what I'm thinking about is this is less than 1. And 1's the key because I know tangent of pi over 4 is 1. This is less than 1. We have an angle that is shallower than pi over 4. Tangent is slope. So our slope is less than 1. It has to be the only angle that we know off the unit circle less than pi over 4. That gives us that x is pi over 6 plus pi k. The period for tangent is only pi. If we have pi over 6 plus pi k, that'll also give us 7 pi over 6, which is the angle in quadrant 3. That's where tangent is positive. Tangent is negative. Tangent is negative in quadrants 2 and 4. So I look at the pi over 6 reference angle in quadrant 2. I've got 5 pi over 6 plus pi k. Plus pi k once again because the period for tangent is pi. Number 4. Yikes. There's a lot of stuff. In fact, there are 2 different trig functions there. One of them squared. What I'm going to do is I'm going to group and then use my favorite F word. I'm going to factor once again. So if I get everything onto one side, we have cotangent of x multiplied by cosine squared, subtract 2 cotangent of x equals 0. Now I cannot immediately add these two because one is cotangent multiplied by cosine squared. This one is just cotangent. It does not have a cosine squared. What I see is this is very similar to working with polynomials. I've got a cotangent term here. I've got a cotangent term here. We shall factor that out. So if we factor cotangent, we've got cotangent x multiplied by cosine squared minus 2 equals 0. What that does for us is it enables us to use the zero product property. If we have the product of two things equal to 0, then we need to find the value of the variable that makes each individual factor equal to 0. So I'm going to set cotangent of x equal to 0. I'm going to set cosine squared of x minus 2 equals 0. Now we've got two statements that are just one trig function. If we're looking for all solutions, cotangent of x equals 0, remembering that cotangent is the x over the y around the circle. That's going to give us pi over 2 plus pi k. Pi is the period of cotangent. That'll give us everything in there. Cosine squared, well, I'm going to get cosine squared equals 2. Take the square root. Cosine equals plus or minus square root of 2. And at this point, I know that cannot happen. That's not possible. Plus or minus square root of 2 is, well, if we forget the negative, that is greater than 1. Likewise, negative root 2 is less than negative 1. And we know that the range of cosine is from -1 to 1 inclusive, and if this is greater than 1, it's outside the range. If this is less than -1, it's outside the range. That's not possible. So for this equation, we have that set of solutions. Number 5. We've got a square term. We've also got two different terms, but they both happen to be sine. Here we have something that is a quadratic trigonometric function, and it's going to work just like a quadratic equation would in the past. If we forget for a moment and we say this is like 2x squared minus x minus 1 equals 0, we would remember from past experiences that we can factor. We would break this apart into 2x and x equals 0. Well, I know 2x and x because I need two things that multiply to 2x squared. I see -1. One of these has to be +1. One of these has to be -1. So I'm going to have x minus 1, 2x plus 1. I know that works because if I check it, I've got -2 when they multiply the outer terms, plus 1x gets me negative x. 1 and negative 1 gets us negative 1. We know how to solve this as a polynomial, but this is not what we have. Going back, 2 sine squared minus sine x, well, we need two things that multiply to sine of a squared. We need things that multiply to sine of x. It works exactly the same as in, now I can substitute 2 sine x plus 1. Sine x minus 1 equals 0. Rather than just being x, I've got sine of x and sine of x. Checking that this works, 2 sine x times sine x gets us 2 sine squared. It's going to be minus 2 sine plus sine gets us minus sine. 1 times negative 1 gets us negative 1. Same like last one, using the zero product property, I can now set each individual factor equal to 0. Solving, we have sine of x equals negative 1/2. We have sine of x equals 1. We know that sine is negative in quadrants 3 and 4. Negative, or 1/2, is the pi over 6 reference angles. So we have x equals 7 pi over 6 plus 2 pi k, or x equals 11 pi over 6 plus 2 pi k. Plus 2 pi k because 2 pi is the period of sine. We've got those two from that factor. From this other factor, we've got sine of x equals 1. That happens straight up. So we've got x equals pi over 2 plus 2 pi k. Now I've got an example where it's again a quadratic, but I am in different terms, different trig functions. Here's where we need to use our identities to rewrite this in terms of something that's only one function. Now cosine of x, we can't very well easily rewrite anything, but sine squared, I'm going to take advantage that sine squared is 1 minus cosine squared. By substituting that out, we've got 2 times 1 minus cosine squared plus 3 cosine minus 3 equals 0. Distributing, simplifying, we've got 2 minus 2 cosine squared plus 3 cosine minus 3 equals 0. And by combining terms and simplifying, we have 2 cosine squared minus 3 cosine plus 1 equals 0. It's again a quadratic term, so I will factor 2 cosine of x, multiply to positive 1, so I know that they need to be the same signs. That's negative, so I'm going to have minus 1, minus 1. Checking, that's 2 cosine squared. Minus 2 cosine minus cosine is minus 3 cosine plus 1. Setting each factor equal to 0, we've got 2 cosine of x minus 1 equals 0. We've got cosine of x minus 1 equals 0, and we'll take each individual one. Cosine of x equals 1/2. That's going to happen in quadrants 1 and 4. So I know that is pi over 3 plus 2 pi k, or I know that that is 5 pi over 3 plus 2 pi k. For the other factor, we've got cosine equals 1, and that gets us 2 pi k. There we go. Give it a go, try it out. See you tomorrow with some more.